Hello, everyone. So today we're going to be defining entropy on pretty much a nice fine-tooth scale. So this is going to be bringing up some important ideas from statistical mechanics that we'll make use of towards the end of the semester, but are important in developing a good understanding of entropy. So let's go ahead and start by addressing the elephant in the room. Whenever people tend to talk about entropy, what we are talking about is usually a measure of disorder. We say that entropy increases if the disorder of a system increases. But that's not quite right. It captures a lot of the important features, but what it kind of misses is some of the important details that really matter for chemistry. What entropy really is just a measure of how many possible states the system can be in. So essentially, a system has more entropy, essentially the more possible ways there are to organize it. Now, if I have a very well-organized system, there's only one place for everything to be. So it tends to have a low entropy. But if things can be found anywhere and every point is as good as any other, then the system has lots of different states it can be in, which means it has a much higher entropy. And this is one of the reasons why we tend to say that the entropy favors disorder, is because disordered systems tend to have a lot more possible ways to be organized. And so we can encapsulate this important idea of possible states by looking at what's called the Boltzmann formula of entropy, where what we have is entropy is equal to the Boltzmann constant, so this is our good old friend, times the natural log of W, where W is the number of microstates, or again, the possible states my system can be in. And it turns out this number is usually astronomically huge. So let's go ahead and look at microstates on a much more kind of fine-tooth scale. So let's say I have a system. So I have, say, a small box, a small volume of gas, where my individual molecules might be found in one of 16 locations. So I can go ahead and then expand this system. So expand my volume to, say, double it, or increase it so it goes up to 24 locations. So now my system is essentially much bigger, has almost twice as many possibilities. Well, let's go ahead and say I now have 4 particles that I went ahead and put into my system. Well, what I want to do is figure out how much my entropy is going to change if these 4 particles can now occupy this much greater volume with its increasing number of locations for the gas to be found in. So what we can do is look at this favorability by examining my number of microstates. Because again, the greater the number of microstates, the greater the entropy. So just from kind of brief examination, if I've got only 16 locations for the molecules to be beforehand and 24 after, we'd expect my entropy to increase a lot because my gas has now more possible arrangements that are all equivalent to where I started. Now, we can go ahead and for simple systems like this, if I allow all 4 atoms to be in one box at a time, the number of states is simply going to be the number of boxes or locations I can put my particle times the number of objects I'm putting in there. So if I can allow any number of molecules in any number of boxes, then, well, it's just simply the number of boxes times the number of particles for the number of options. So for my initial state, this would be any given molecule can be in one of the 16 boxes. And I've got 4 of them, so it's just going to be 16 times 16 times 16 times 16. So this gives me 6.6 times 10 to the 4th possibilities. Whew, that's actually quite a lot. But if I increase the size of the system, there's now, sorry, I miscalculated this, 32 possibilities. And then what we see is a drastic increase in the number of locations for the particle. So my entropy is going to go up drastically. We can also essentially modify this if I only allow a single atom per box, because now what I have is the same number of original possibilities, plus I have to factor out how many boxes have already been occupied. So then we can give my number of microstates is equal to the number of objects times the number of particles divided by the number of particles factorial. So we see again many less available microstates, but in general what we see is that as I increase the volume of my system, I tend to see my number of microstates go up drastically. And this actually brings us to a very important point. In general, if I increase the volume of any system, my entropy is in general going to go up. This is just a natural feature of entropy. So this is why we tend to see that most systems want to expand, because unless there's something telling me that these particles want to stay together, the surest way to increase microstates is to expand the volume. And as we increase the microstates, we increase entropy. So this is an important thing to kind of keep in the back of your mind. If you want to figure out whether something is going to be favorable or how much it's going to be favored by entropy, think about how many arrangements I can put the system in. Now, one of the things I do want to make note of this second equation for if I'm only putting a single atom per box assumes that I have a relatively small number of objects with regard to number of boxes. It is worth noting that as my system becomes fuller, it becomes the empty spaces that are more important in determining microstates than occupied spaces. But it helps illustrate an important point of trying to figure out the number of possible ways I can arrange a system is going to have a direct impact on how favorable a system is. Because in general, things like to be flexible. They like to have as many possible arrangements as they can because, well, it's just more likely to happen. The more possible states the system can be in, the more likely it's going to be in one of those states. And in general, what we're also going to tend to see is as temperature is that this idea of entropy is also going to be kind of related to our Boltzmann probabilities. So again, what we see here is that the likelihood that I'm going to see a particle in any given state is going to be related to the exponential of the negative energy of that state divided by the Boltzmann constant times the temperature. So we've talked about this Boltzmann arrangement beforehand, but it actually ends up showing us something very important. If I have a low temperature, what it means is that I'm only going to be able to occupy states with very low energies. Because as my energies go up, I'm less likely to see that state occupied unless I have enough energy to occupy that state. And again, the more states I can occupy, the higher my entropy is going to be. So in general, what we're going to find, temperature goes up, this dampening factor goes down, this number gets closer to, the probability becomes closer to 1, and this means that I'm going to have more states that I can occupy. So in general, this ability to occupy more states, more high energy states, is going to end up leading to a higher entropy. But it's worth noting that as my temperature essentially gets high, as I slowly increase this temperature, I see a smaller and smaller fraction of new states essentially become occupiable. And so I don't see as much of an increase in entropy as I go to higher temperatures. So we can examine this a little bit more visually. Let's say I've got a very low energy or low temperature. And so most of my system is going to be in a ground state. where E is 0. And I got uh, one or two molecules in this excited state, where this E is still fairly low. Then I add in some energy, my temp goes up, and then I slowly can occupy a few more states. But this is way more microstates than I started with. So my microstates go up a fair bit, but as a fraction, this is a huge fractional increase. Now, if I start at a high temperature, then I've already have a fairly high number of microstates. I add in that same amount of energy as heat, and I get many more microstates than I originally started with. But as a fraction, it's hard to tell the difference. And so this leads to an important idea we're going to be talking about a lot, which is more or less the idea that at higher temps, the influence of adding a little bit more heat is going to increase the entropy a little bit less than we saw before. Now let's look at this kind of a little bit more numerically, dealing with an idea that we'll talk about more next semester, with talking about the quantization of states and energy. So let's say I've got 4 particles, and they can be located in one of 4 states, or one of 3 states. One with an energy of 0, an energy of 1, and an energy of 2. So if I start as low temperature as I can get, and my total energy is 0, all 4 particles are going to be in this ground state. Now, in this case, the number of microstates, or the number of possible arrangements of these 4 particles that will get me this energy, is actually fairly easy. There's only one possible arrangement: everybody in the bottom. So this gives me an entropy of 0. Woohoo! And so again, not exactly the most favorable case. Now let's see what happens if I add in 1 unit of energy. So now my energy goes up to 1, and now I'm able to take 1 particle and move it up. Now here's the real trick. My microstates is now gone up to 4, because I've got 4 particles. One of them's up there, but I don't know which one. So I've got 4 different arrangements that will still give me 1 particle up high and 3 down low. So my microstates went up to 4, and my entropy is now Boltzmann's constant times 1.4. Now let's add in that extra degree of energy. So I add in 1 more unit of energy. I can go ahead and pop this already excited particle up high, or I can take one of these guys and pop it up to the medium level. Well, just like I have 4 states that can give me this configuration, I also have 4 states that can give me this configuration. And it turns out, I'm not going to work through the math, but you can do this example by hand. There's 6 possible configurations that gets 2 particles up in the second level and 2 particles down at the ground state. So again, what I have is a 4 microstates in this first case, 6 in the second, with a grand total of 10 microstates for having an energy of 2. And this gets me a entropy of 2.3. Now, one of the reasons I wanted to go through this is because it illustrates the point that I had previously. If you're at a very low temperature, any small amount of heat increases your number of microstates and thus your entropy by a lot. My entropy went up by 1.4. But when I add that same energy at a higher temperature, so now instead of a very low temperature, I'm at just a low temperature, what I saw is that my entropy went up by 0.9, so much less than I had from the first unit. And we're going to see this happen quite a lot. That entropy is going to be dictated by essentially 2 features: how much heat I put into the system and how much energy was already there. So we typically describe this as the heat being added and the temperature of the system will essentially give us will give us information about the entropy of the system. So We're going to be trying to scale this up more to a thermodynamic level next time. Till then, take care.